Treewidth, one of the major outgrowths from the beautiful work of Robertson and Seymour on graph minors and immersions, was the exploration of a new parameter which measures in a precisely defined sense how tree-like a graph is. The fundamental idea is that we should be able to lift many results from trees to graphs that are tree-like. The extent to which Robertson and Seymour's intuition has been vindicated is quite astonishing. In the present section, we will look at a new parameter, tree widths, and associated parameters such as path widths. Later, we will look at the uses of bounded tree widths for algorithm design. We remark in passing that the notion of tree widths seems completely intertwined with the computational issues, as we see with Corsellis and Cece's theorem later, and as can be seen by, for example, Thorup. The best known definition of tree widths comes from partial K-trees. Definition 6.43 K-tree. The class of K-trees is the smallest class obeying 1 and 2 below. 1. K plus 1. The complete graph on K plus 1 vertices is a K-tree. 2. If G is a K-tree and H is a subgraph of G isomorphic to KK, then the graph G' constructed from G by first adding a new vertex V to G and then adding edges to make H union the set V a copy of K plus 1 is a K-tree. B. If G1 is a subgraph of a K-tree, then G1 is called a partial K-tree. Example 6.44. In figure 6.15, we give examples of 2 trees and 3 trees. Definition 6.43 leads us to a very important concept. Definition 6.45 Tree widths. We say that a graph G has tree width k if k is the minimum positive integer such that G is a partial K-tree. For algorithmic purposes, definition 6.45 is not the most useful. An equivalent characterization of tree widths is provided by the following. Definition 6.46 Tree decomposition. A tree decomposition of a graph G equals to V is a tree fancy T together with a collection of subsets Tx called backs of V labeled by the vertices x of fancy T such that the union of Tx for all x in fancy T equals to V and 1 and 2 below holds. The first condition 1. For every HUV of G, there is some x such that the set UV is in which is a subset or equals to Tx. The second condition hold is the interpolation property. If y is a vertex on the unique path in fancy T from x to z, then Tx, the back Tx intersect the back Tz, which is subset or equals to the back Ty. B. The width of a tree decomposition is the maximum value of the size of Tx minus 1 taken over all the vertices x of the tree fancy T of the decomposition. Before continuing our analysis of tree widths, we remark that there are a number of important variations of the notion. See e.g. Botlander and Angelfried. One of these is to tree decompositions what regular languages are to regular tree languages.